A comprehensive guide to GC. Warning: this video includes everything you need to know about GC. Once you watch this video, you'll be dying to know the next series. Before getting into the carrier gas and basics of GC, let's see how GC is configured. Generally, GC is configured with carrier gas, an injector, which can be a manual syringe or autosampler, an inlet, a column, an oven, a detector, and a CDS, chromatography data system. Once each module is configured into a GC system, it can show how the flow goes through a GC. The carrier gas flows into the column passing through the inlet. When the sample is introduced into the inlet, the carrier gas sweeps the sample onto the column. Then, the sample is separated into individual components through various chemical interactions with the stationary phase in the column. And then, the detector converts the concentration of each component into electrical signals. Finally, the signals are shown as a chromatogram by Chromatography Data System. Let's look into GC carrier gas in detail. What is the carrier gas in gas chromatography? The carrier gas is an inert gas used as a mobile phase to transport the vaporized sample into the column. Carrier gas can be supplied by a gas cylinder or a gas generator. What are general requirements for carrier gas? First, carrier gas should be pure. Pure carrier gas means there are no impurities in it. To keep the purity of carrier gas, traps are recommended to use in gas lines for the removal of impurities such as moisture, hydrocarbon, and oxygen. Carrier gas must have a high purity standard of not less than 99.9995%. Second, it should be chemically inert. Being chemically inert means there's no chemical reactions between carrier gas and either samples or stationary phase in the column. Then which gases are commonly used as a carrier gas? There are three major gases we use for carrier gas: hydrogen, nitrogen, and helium. They all meet the requirements of pure and chemically inert. Plus, the carrier gas should be selected depending on the detectors and analytes. Select the carrier gas based on GC detector types. Each detector requires specific carrier gas types based on its principle of detection. For example, the pulsed discharge detector, PDD, requires helium because it has the largest ionization energy. The recommended carrier gas for GC detectors is shown in the table below. Select the carrier gas based on your analyte types. The selection of carrier gas needs to be different based on the type of analyte you analyze. For example, if you analyze nitrogen, you cannot use nitrogen as a carrier gas because the analyte, same as carrier gas, cannot be distinguished for the detection. Then why should we use high purity of carrier gas? If you use low purity of carrier gas, it will cause unstable baseline with drift, relatively lower sensitivity due to high noise. But when you use high purity of carrier gas, you get more stable baseline and better sensitivity through a high SN ratio, compared to the chromatogram data in low purity of carrier gas. Before choosing the right carrier gas, we need to know Van Deemter equation. Let's refer to Van Deemter equation to understand how the separation efficiency is determined. Van Deemter equation is a relation between HETP and linear velocity, and each term A, B, and C defines each band broadening mechanism to determine separation efficiency. The values of A, B, and C will be different based on gas type, so the efficiency is up to which carrier gas you choose. Let's find out each term's band broadening mechanism. First, term A, eddy diffusion. Eddy diffusion describes each analyte takes different paths through the stationary phase at random. These various moving paths of analytes might cause band broadening and eventually reduce the separation efficiency. Second, Term B. Longitudinal diffusion. Analytes diffuse out from the center to the edges as mobile phase flows, so it also causes band broadening. In case of GC, longitudinal diffusion, which is term B, has much more effect on separation efficiency than LC because gas phase is more diffusive. Last, term C, mass transfer. Analytes take a certain time to equilibrate between the stationary and mobile phases. This also results in band broadening. When the band is broadening, the plate height is getting higher. As a result, separation efficiency is being decreased. In conclusion, the lower value the HETP has, the greater separation efficiency it results. The plot of Van Deemter equation is shown on the screen. A range marked in bold line of each gas indicates its optimized linear velocity range as a carrier gas. So now you can choose the right carrier gas depending on your application by referring to the following table. Safety. Hydrogen is not safe due to a possibility of explosion, while the other two gases are relatively safe in use. Cost. Hydrogen and nitrogen are cost-effective, but helium is expensive. Optimum velocity. 35 to 40 centimeters per second is recommended to use in hydrogen, 25 to 30 centimeters per second for helium, but 12 to 20 centimeters per second is recommended to use for nitrogen, which means it has a longer analysis time than other gases. Column choices. Helium can have a wide range of column choices, from wide to narrow bore. Lastly, there are various detector choices by carrier gas as shown in the table. Find the right carrier gas by referring to this informative video. Want to learn more about chromatography? Please stay tuned on Young in Chromas channel.